let me start with on the client and kind of how it works and talk about philosophy a little bit and how we've kind of structured things. And then I'll move into general chemistry first and use the inorganic qual lab as an example. Then I'll go into organic and kind of show how organic works. And then I'll go back to general to show some of the other labs quickly. Is that okay? All right, so I'm going to share my desktop, and we'll minimize that and close this up so I can get some screen real estate. All right, so we started developing these labs back in 1998. I had the original idea as a graduate student at Berkeley when I was teaching their Chem 1A class, and the students were doing inorganic qual and they were learning nothing, right? They were just cookbooking. And I had maybe my one original idea in my lifetime, which was, students in a real lab, students are constrained that we have to give them procedures and we have to kind of guide them along in a highly structured environment because we don't have the time or the resources or the safety to let them kind of explore. And so, I've always been kind of, used computers a lot in research. And so I figured out an algorithm where I could kind of create an open-ended qual scheme that would allow them to make the same decisions. But I realized that I couldn't teach them technique on a computer, but I thought that the computer would be really good at allowing students to make decisions and suffer consequences. So for me, at least my philosophy in teaching, and a lot of people have a different way of saying the same thing, so I don't think I'm original, but students really learn by failing. They really learn by making mistakes and figuring out where the mistakes are. So the whole kind of philosophy behind the labs is allowing students to have the choices they would really have and then see what the real results would be. So we started these labs in '98, and they've gone through about 4 different iterations and translations into different platforms, updated graphics and stuff. And so right now we're Mac and Windows, and we're working, when we get the bandwidth, to convert into an HTML5 format. But for now, they're Mac and Windows. So what we did last year is, these things used to be sold by Pearson for many years, for like 15 years. And we took our licenses back from Pearson and started Beyond Labz last year. And what we did is we created this client that you can see, which you guys probably all seen. And it's just a wrapper around managing the downloads and installations of the different lab products. And just to make it 1-click, 2-click installations and make it easy. So this first tab here is just the lab. So I've installed them all. And so you just click on the download and installs. We have about 2% of the cases, students' Windows operating systems have been corrupted. Who knows what they've done to them? Their registry is all messed up. And so sometimes the install doesn't work, and we have how to fix that, but just giving you a heads up that there's a few students that run into problems on Windows and a few on Mac when the download gets corrupted. But by and large, you click, you install, and now you have access. This is where we house our worksheets, and on the worksheets tab, so each product has a different level, high school and higher ed. So choosing a different level doesn't change the simulation. It just changes the worksheets that are available. So our philosophy is kind of like a lab room where you have a bench, it has drawers full of equipment, stock rooms full of equipment. And so at each one of our benches, we allow essentially an open-ended environment so students can do anything. So obviously we can't throw a student into the lab and just say learn. We have to provide the pedagogical structure. And that's what these worksheets are. So we have high school level, we have higher ed level, and then we group them into different topics. So for example, if we want to focus on descriptive chemistry, then here's some descriptive chemistry worksheets that we have. And but by no means are these worksheets a complete set of what the labs do. These are just a small set, and you're welcome to adjust, modify, write your own, do whatever you want. This is just where they live. So this is just kind of how you get to them. So in descriptive chemistry, if you wanted to do cobalt, chromium, copper, you know, as an unknown, then here's where the worksheet would be. And so these are PDFs. We can give you the Word versions of these so you can modify them. You're feel free to download them off of our client, put them onto your LMS. But you notice that there's pretty good procedures here, and some of the worksheets have a lot of procedures, some have fewer procedures. So we're trying to balance where we are on Bloom's taxonomy and what you're trying to do. So they're kind of built to work together. This tab is where you put in your license code. I believe that code's out. You would just put it here, submit the activation code. Should be good for a year. Some students, just to give you a heads up, some students put the code in and we don't say success or anything. We just kind of put the license code in with an expiration date, and because we didn't give them a pop-up saying, hey, successful, they think it wasn't successful. So you can tell it's successful if you see an expiration date for a year later. Settings is where you set the level. Again, it doesn't change what happens in the lab. It just sets the level of the worksheets, and I'll show you how that works. It won't be relevant to you, but some student may come up and start messing around, and you need to know why. So this just lets you set the different levels, which corresponds to the different level of worksheets that we have. All right, so that's kind of how it works. So I'll go into general chemistry and launch it. I'm going to change my screen resolution because I have a pretty high resolution monitor. So I'm just going to make it a little bigger just so it's easier for you to see on the screen sharing here. So this is our landing page. Each one of these icons represents a lab bench, all right? You also have a lab book here that you can click on, and you can do it inside the labs. So this is where, you know, students can take notes and save those notes, so they can go to file and save it and then open it later. I'll show you a little bit more about that in a minute. Help files, no one ever reads these, but they're pretty detailed. And over here are these worksheets again. Okay, so one way, a common way of using the labs is to just use our worksheets. So you notice that these are organized in the same way as the worksheet tab was for higher ed. So when you pick higher ed, you pick this set of worksheets. When you pick high school, you'll pick another set of worksheets and in a different table of contents over here on the left. That's the only difference. And so if I come back down here to descriptive chemistry, you know, and I wanted to do that same worksheet, the instruction would say, go to the worksheets and select identification of cations in solution, cobalt, chromium, copper, and they would click on that. And what it would do is bring you to the inorganic lab bench. Okay, so so that's just how it works. We have the ability to do presets, so we can pre-configure the labs into different configurations based on the worksheets, or also based on common types of experiments or common or famous experiments they may want to do. So each one of these, you know, icons here lets us go into these different labs. So if I did titration, you know, like I said, it's like opening a door. Here's a lab bench. Here's a drawer full of beakers, a drawer full of pipettes. Here's a stock room full of chemicals, and go at it, right? The worksheets provide the directions of what to do. We also have here these presets. So clipboards contain common or importantly used experiments that sometimes we hook up to our activities. So for example, I can click here, and instead of forcing them to set up the entire titration experiment, it's preset and all ready to go. So I've got Sodium bicarbonate's been weighed out. It's already in the solution. I've already picked an indicator. I've already got my pH meter calibrated, my conductivity meter, you know, here's their values. I can click save and I can actually start going through and doing an experiment. I'm saving this data. Here's my lab book, tells you how much was added on the beaker. And so this is just a way of doing this experiment. So we have a graph. So I'm not going to go into details. This just kind of shows you, you know, how all of the labs work. So they're all kind of structured in that way. Worksheets here, clipboards for presets, all open-ended. So even though that's a titration lab, you know, we have other activities that use the conductivity meter to talk about strong and weak electrolytes, or we'll talk about acid-base properties or buffers and things like that. So lots of different activities you can do. So you guys want the inorganic qual. So I'll go back in and I'll show you how this works. So this was our first one. You're seeing the fourth iteration of it over time, but it's the same underlying engine. So what you can do is pick a test tube, all right? So it's an empty test tube, and we're gonna show you a real picture of what's here, all right? So now I can add any of these cations, any order, any combination, all right? So, so if I go and I add copper, for example, then I'm going to show you a real picture. And then down in here, I'm going to show you the current state of that cation in the test tube. So I can add cobalt and you'll see a real picture. And then I'm going to add chromium and you'll see a real picture of what that mixture will look like. So once I've done that, I can add any of these, any order. So for example, you know, if I go add something like bismuth, all right, you know, it's going to come over here and it's going to automatically form a precipitate here. And I'll show you a picture of what that looks like. Now, I don't want it to do that. So I'm going to take it to my disposal bucket and get rid of it and add a new one. I can label my test tubes. It shows up here on the label. And so I'm going to go add my cobalt, chromium, copper, and start over again. So now I can do any of these lab manipulations. So I can centrifuge, flame test. So for example, I do a flame test right now, and I'll show you a video of and you'll see the green copper flame. I can do a flame test with a cobalt filter in front of it. So that's good for sodium, potassium. I can decant, I can make a copy. So there, I just made a copy of that test tube. I can heat, so I can heat up my solution, change my reactions, pH of the solution, pH of the vapor. So here's my pH key. I can smell it with the nose here, and I can stir it. And then I can also add these 11 reagents. So I can add these reagents, any order, any combination. Now, obviously, it's not a complete set of reagents that we might have access to. But we were looking at allowing for all combinations and permutations. So there are 10 to the 26 combinations and permutations in this lab. So we limited our reagents to the basics in order to do a complete qualitative analysis scheme for all 26 of these cations. So we have nitric acid, buffers of 4, 7, and 10, sodium hydroxide, sodium carbonate, sulfates, chlorides, sulfides, ammonia, and peroxide. So we're covering all of the chemistry that we would cover in general chemistry. So we're doing acid-base chemistry, precipitation, complexes, and oxidation reduction. So we allow for any order, any combination. So this is all based on real data. So we had students, I had 4 students work for 2 years, averaging about 100 hours a week for the 4 of them, doing all the permutations of these cations and how they affect each other and inside these test tubes, and then taking real pictures and video of the results. So this is all real. So it's kinetically based in the sense that some reactions might be slow. So they may add it and the solubility tables may say you're supposed to get a reaction. Calcium sulfate's a classic. it's insoluble, but it takes 3 days to it to form the precipitate. So we don't show that precipitate unless you heat it up, for example. And so all of that real chemistry is going to be in here. So this is how, for example, we would do this. So I could go and say, hey, what happens to pH 4? Or what happens if I go to pH 7? Or what happens if I go to pH 10? And then I can show, hey, all of these things are forming precipitates. There's their current state. So these are real chemical states. Like you may say, hey, nitrates are insoluble, but cobalt forms a weird nitrate precipitate with hydroxide. We did this. We determined that thing spectroscopically. And then I can go to, say, sodium hydroxide. Notice I added sodium now to my cation list because I added sodium hydroxide. If I do a flame test, for example, now you're going to see the sodium flame. I can centrifuge that. I can then, I can notice that chromium went into solution just because it's amphoteric. So I can decant and separate that. Now I'm left with my cobalt and my copper. Students would have to explore. Maybe you tell them, or maybe they explore the different chemistries. Cobalt and copper are really similar. So I'm going to go add ammonia. And what I'm going to note here is that at really high pH, the cobalt wants to form a hydroxide instead of an amine complex. If I go to pH 10, I'm going to get both amines. So this is a way I can separate and identify. So I'll centrifuge, decant, and so there's my copper, here's my cobalt, and I can go, hey, here's my pH 10, here's my, I can add some carbonate and look at a cobalt carbonate and be able to learn all of this chemistry. So I want to show you some other real stuffs. It's common for, from some people to say that we have an error in our, we may have some bugs, but in terms of the algorithm for this, it isn't. So for example, here's chromium. So the purple color comes from a certain D-level splitting from the water ligands on it. But what's interesting, if I go to an acid and click, if I go to base, sodium hydroxide, and click my peroxide, I'll oxidize it up to my chromate. But then if I go back to the acid, I'll go back to the chromic ion, but notice it's green instead of purple. By oxidizing and reducing again, it changes the ligands, it changes the D-level spacing, we change the color. So this is real chemistry, again, not predicted based on solubility tables. All right, how do you do unknowns? All right, so there's several options you have here. Older versions in the 2000s, we had a back-end system that allowed you to customize your unknowns, but nobody ever used it, and it took half of our resources to manage it. And so we kind of did away with it. So, but we have options for unknowns here. So let me clear all of that by clicking on the disposal bucket. So I have here this unknown sign. So I can click here. And what it does is it gives me the ability to randomize options. So I can pick cobalt, chromium, copper. So I can pick the cations I'm interested in, and then I can define my randomization parameters, right? So I can say I want a minimum of 0, which means water, or I can have up to a maximum of 3. If I go more, it won't work because I don't have 4 cations, and so I can go create an unknown. So here is what we call a practice unknown. All right, so you can define any unknown combination you want here. Okay, so we call it a practice unknown, but it doesn't have to be. So this is an unknown, it's hidden. And so I pretty much know right now that that's water because it's colorless and all the other cations were colored. But they could go through and, do the test. I can go to pH 10, I don't get anything, so I know it's water. Then what I can do is go to my lab book, and I can click here on report, and I can just click the ones that are present. I don't have any of them, click submit, and I get all green, so I know it's right. So here is a practice inorganic report. What students can do, our intent here was for students to practice develop their own schemes and practice with their own practice unknowns. until they think they were ready for a real one. But if you have a custom set of unknowns that you want to define out of these cations, you can tell them how to define that set, and then have them do the unknown and then report. Yes, there's ability to cheat, and then there's some other things that could happen, but um, but you know, you can do it this way. And then what you do is you can click here and click on save, and I'm going to save that, and then what can happen, so I'm just going to exit it out of here. So here's this lab book. What students can do is then send that to you, upload it to your LMS, and then you can, it's a proprietary format because we have copyrighted data in it that we can't make it public as a PDF or a Word doc or something. So what you can do is come in and open a clean lab book, like right here, click File, Open, and then I can double click on that, and then here's the data, and you can look at their results, or students can keep their results in their lab book and then add to it over time. So that's just an option. So that's option number one, practice unknowns for students to practice, or you can define any combination of these cations as you want. The other unknowns exist. There's 3 different kinds of unknowns on the clipboard, okay? So we have what I would call pretty basic ones, pretty simple. If you mouse over, so for example, alkaline earth metals, I click on this and I can preset a known, where's the label, and they can see, so they can go around and say, hey, I'm going to go do the sulfate. So I'm going to go to acid, add the sulfate, barium comes out, centrifuge, decant, you know, I'm going to come over here and switch it. And now I'm going to go to pH 4 and pull out the strontium and so on. They can practice. Then what they can do is come over here and then do the alkaline earth metals unknown. And so now you see that unknown shows over here, but it's in the left slot. And so I can bring that, but this is a numbered unknown. All right. So if I go to the lab book, all I can do is finish it. I can't report it here. This is unknown 12. So we have a key in our instructor manual that will tell you what's in unknown 12. So these are randomly generated unknowns, but they're the same for each computer. So in other words, if I do it over and over again, I'm always going to get unknown 12 if I'm on this computer. So a student with this installed on their computer is always going to get the same unknown, so they can't go through and say, oh, I don't like that one, I'm going to go get another one. They can't do that. So we have these what we call these numbered unknowns. So that's one way of doing it. A second unknown would be what I call these advanced random ones. So these are predefined sets. You can mouse over and see what cations are in each ones. But these are built to guide students into doing a full cation set unknown, all right? 25 of them, everything except ferrous ion. And so you start with these simple ones, you start with sulfates, you start going into the different groups, and we build them. So this is what I do for my lab class and my general chemistry classes that I teach, is I teach all this descriptive chemistry by having them do qual schemes and learn that chemistry through here. And so by the end, I will give them as their exam almost their full cation set. And, you know, they get really stressed out about it, but the average result is usually 90%. That's the average. So they do pretty well on this ion. So I can come over here and say, hey, I'm going to pick my acidic sulfides. Here's my unknowns. And then they're going to go through and have to go do that. This unknown, however, notice there's no unknown number. This unknown is reported. I know I have at least bismuth because of the precipitate. And so they can go report that, put it in the lab book, upload the lab book to you, and grade it. So that's what I do. The last option is the same unknowns as before, the same advanced ones, except everybody in class gets the same unknown. So these are fixed. Um, and so that just means everybody gets the same one, so it's kind of easy. Of course, the downside is once the answers get out, then you really can't do it, but that's just another way of doing it. So that's the inorganic qual. Any questions? Go ahead and ask questions because we're a small group.
Brian, why is, you mentioned that you didn't have, for example, cyanide, ferrocyanide. Any reason for that in general, or?
Oh, yeah, what happens is that, what happens is the, with all the cations, I think it's the presence of the silver, the possible presence of silver will oxidize the ferrous up to ferric, and you'll never know if you have ferrous or ferric ion in there. So I only start with the ferric and that unknown. So having other possible cations can oxidize this up to ferric, and you can't distinguish between the two. Some of the smaller sets, we do include, expect them to separate ferrous from ferric.
Brian, you had said earlier that when the students are assigned an unknown number, that it remains the same unknown number regardless of how many times they start it, like the unknown number is assigned to the computer. So if the student exits the program, closes the web client, and reopens it, they'll still have that same unknown number?
Yes. So which one did I do? I think I did this one. And so, well, I don't think I did that one. Yeah, they should be the same one over and over again. What we do is the random number key is generated off of their hard drive serial number. So that just means that we'll get the same random number every time based by using the same key. So we don't use the time of day as a key. We use the hard drive serial number.
Okay.
So in the instructor manual, which we can give you, I don't know if I've done that yet, Nala, I can send those to you if you just send me an email, is we have all those answers.
That would be great. We don't have it yet. Thank you.
Yeah, it has answers to all the worksheets as well.
Thank you.
All right, are we good with this one? All right, let's go to do organic chemistry. So I'm not an organic chemist. What?
Just one quick question. Obviously, there is a tremendous amount of, we have a steep learning curve for this in order to kind of be able, for example, to have some unknowns deployed by next week and stuff like that. Do you guys have like a customer service type or a phone like help type thing in there, or you're too small to have, given all the volume that you have right now?
Yeah, that's a good question. So it is, we are very busy, yes, but we do have, we do have the contact page. So if you go to a contact page on our website at beyondlabz.com, and you go to the contact or contact us, that will get to us and we'll answer you within, I don't know, within several hours, we'll be able to answer any questions. But onboarding can be pretty easy. I mean, I've been doing this for a long time, and I've been teaching freshman chemistry for 22 years. And so we all know the trade secrets of teaching general chemistry. That is, there are some smart kids and there are some kids without common sense, right? And students without common sense. And, we always have those. They're always going to be with us. And so we've got some videos and some onboarding things to help them out. But the best way to go get started is to say, do this simple flame test worksheet. It gives them a little bit of background, and then it says start virtual ChemLabs, select descriptive chemistry, and then select identification of cations. in solution from the list of assignments, and the lab will open the inorganic lab. And then it goes through and gives them step-by-step instructions of what to do. And then it says, okay, you know, depending on the, you know, here's some practice ones. And then, okay, when you're ready to go do it. Here's your unknown number, what cations are found. They can take a picture of this and upload it to your LMS or whatever. And so you really don't have to do anything. You just say, go do this worksheet. And there's not a lot that you have to do. Now, if you're trying to get the lab configured to match up what you're doing in the real lab, that's going to be a little bit more work. But like I said, we can provide these worksheets as a template, and then you can modify them as you need to. All right.
Thank you.
Organic. So like I said, I'm not an organic chemist. I had a colleague of mine, Merritt Andrus, who is an organic chemist. I mean, he's like hardcore. We actually developed this our first year at BYU 22 years ago because we were bored at a new faculty week-long seminar. And so we kind of designed this all together. So same structure, okay? Lab books, help files, exits. We have 2 lab benches, synthesis and qual, all right? And then we have these worksheets all grouped together. So I always recommend this one first. This just teaches an simple esterification reaction, shows them all the steps to do a synthesis, how to do TLC. Doesn't have any spectroscopy in it yet, so it's a great organic one, kind of early thing to do. Yes, this lab has a lot of possibilities and what you can do. So what you do if you're early in organic and they haven't talked about NMR and FTIR and stuff like that, then you just don't have them do any of those kind of things. But we do have all of these worksheets, and they're all pretty much the same. They're all geared around certain targets, certain reactions, certain starting materials, certain reaction conditions that you're trying to teach. We also have some qualitative analysis unknowns that we can use, just like we did for inorganic. We also talk about spectroscopy here. So again, these are not meant to be like match up to your curriculum. They're meant to be a resource that you mix and match and modify and use that fits what you're doing. So I know you want to get to qual, but I think doing synthesis first makes more sense about what qual does and why we do it a little bit. So I'll just do this quickly. So this is a lot busier lab. Each of these simulations, each of these lab benches have their own personality based on the kind of experiments they do. So they all kind of have the same features: lab books, clipboards, disposal buckets, chalkboards sometimes, you know. So here, what we're doing is we're giving a list of these named reactions, and the structures you're seeing are the available starting materials for each one of those reactions. All right, so it's not meant to say, hey, if I pick Grignard, am I only going to be able to do a Grignard reaction? The answer is no. This just selects the starting materials you have available to you in the lab. So if I go to esterification and I click it, then I have these starting materials. So I have some acids and I have some alcohols. I can pick any combination, 0, 1, or 2 of these starting materials. So what I can do is pick this acid and add it. And so you'll see, okay, it's a solid because my solids are on the left. I'm going to pick this alcohol and I'm going to add that. So I've added 2 of them. I can add a solvent, or I don't have to add a solvent. Okay. So I'm allowing anything. So once I've kind of got my starting materials, I'm going to drag my flask to my stir plate. And so this shows me what's in it and their structures. Now, notice that this darkens, so my stockroom is closed. What I can do now is I have these 14 reagents. I can add any of them. So that's the open-endedness of the synthesis. It's just because I pick a certain set of starting materials doesn't limit me to the reaction specified or named in those starting materials. It's just a grouping. And so I can do whatever reaction I can try. I can add none of it. I can add one of them. So I want to do a esterification, so I'm going to add that. And so now I've added it, and you can see here, and I don't have to add it first. Now I can say, hey, maybe I want to add a condenser. But what if they start the reaction with just a condenser? Then it will just run at room temperature. So I can add heat. So the temperature runs based on the boiling point of the materials that I have in it. So adding a certain solvent, I can adjust the reaction temperature and have this condenser. And so we have the kinetics, first or second order. Almost all of them are second order. All the second order kinetics and their rate constants based on temperature. So I can also do a reaction based on ice, with ice on it as well. We also have to put the nitrogen. So if I were to not put the nitrogen and run this reaction, this would probably blow up in about 30 minutes after building up some pressure. So all of the different permutations are allowed here. So the idea is, what starting materials do I need? Notice it's not quantitative. I didn't weigh out or measure the volumes. We assume there's stoichiometric volumes that were added, but I can choose the right reagents, starting materials, reaction conditions, and then when I'm ready, I can click start. And so clicking start starts the reaction. You can see the stirring. Then what I can do is monitor the reaction using TLC. So I can see that I'm making product. Here's my starting material lane. Here's my product lane. And I can save that to the lab book. And now I can sit here and advance my time. So you can say, well, students will just advance their time 4 hours or 10 hours and just get the product. But the trick is to ask them how long did the reaction supposed to take, so that they have to methodically advance some time, do a TLC, save that to their lab book. They can click on their lab book here and say, this was beginning, this was at T equals 20 minutes or whatever, and so on. And so we can go do that again. But it is logarithmic. These aren't linear times. These are second order. So I can do that when I can say, well, maybe I'll just do another one. Notice that my TLC advances my time 5 minutes, okay? Because it takes time to do a TLC. So I can do that. I can go do another one. Finally done. And so save that to the lab book. Now what I want to do is I want to work it up. So what I'm going to do is drag my SEP funnel, and now I have my product mixture here. And now I can do extractions using one of these aqueous reagents. So I can use water, sodium. So if I make an acid, I can add base to go pull it into the aqueous layer and whatever. So I'm just going to use water here, add that. Notice that I've added ether. Now when I do this step, we pull the organic layer off and we assume a rotovap step here. So we take off the ether. Now, this particular reaction made a single product. I could do a distillation. I could, here's my aqueous layer. I'm going to get rid of that. I'm going to go put my SEP funnel back. I could come over here and drag my distillation rig here and distill it if I had a mixture, measure the temperature, collection flask, and separate the two products that way. You can also take a solid and recrystallize it and see the shapes of the crystals and the color of the product that you would do. So I'm now open here. Now I can do my analytical chemistry, right? My characterization. So if it was a solid, I could go do a melting point, but I can now go do NMR on this. So I'm going to drag the NMR. So these are real spectra that we acquired from Sigma. If you notice, all of our bottles look like Sigma bottles. And so you can zoom in, you have the peak identification. Here's the integrations of the peaks. I can save this to my lab book. I can also do a carbon-13. So obviously you're not doing this in organic 1. Maybe you're going to do this in organic 2, but I can do a carbon-13. So if they're not ready for it, just don't have them do that in their in their procedure. Here's mass spec. So we have mass spec again. These are all real data. Here's FTIR and real spectra here that we have. So all of these techniques. So it's all about starting materials, reagents, reaction conditions. How do you know when you're done? What's the kinetics of the reaction? How do you prove what this up here says you made? How do you prove that you really made it and verify that? So any questions about this?
I have a question, Brian. At the point where they're doing the workup and they have the SEP funnel and they're adding some type of aqueous reagent to it, and you clicked on the little waste bucket to toss out the aqueous layer, can they throw away their organic layer like they sometimes do in real life?
Yes, absolutely. Yep. So I mean, I can, let me get back to that point. Let's say for example that they let's get there. So let's say that they came over here and then I add my trace amount of sulfuric acid, and let's say they didn't do anything. I just press start and then they said, oh, I'm done, right? But they're not done. What if they did something like that and they just stopped it right there, right? I have over here my product mixture, and then if I add my, if I did my sodium hydroxide, it should pull my phenylacetate down into my aqueous layer and my butanol. And what if they drag the wrong one? They can drag the wrong one, and so I can pull my organic down here and just throw away the wrong one, or they can pull the water one and drag it here and have both copies here. So there's that. And you should be able to, if I didn't take it out of the SEP funnel, I could have added the acid back to go pull that back into the organic layer, but I didn't do that. So yeah, you can do those type of extractions.
Right, I have a question along the same line. Say, from the perspective of a smart student who is also interested in chemistry and is actually going to use this in order to learn things, have you guys kind of considered all the permutations of the physical and chemical processes that could happen here? In other words, if like a student who wants to learn something, he just goes and takes your sodium hydroxide and puts it on the heater and he heats that. Do you have those eventualities thought of, or these are very structured in terms of the pre-written scenarios?
So yes and no. We attempted to be as open-ended as we could be given the constraints of the time and resources we had available to develop this lab. So for example, this lab had 6 undergraduate students for 2 years working on creating the database of all the reactions and outcomes and spectra and all that kind of stuff. So we actually had to account for about 4 million different possible outcomes of what they could do by the different starting materials. So we do allow for a lot of that within the context of what we're trying to target in terms of learning in this lab. So any of these, so we're going to allow them to pick any combination of those starting materials with any of these reagents under any of these reaction conditions. Yes, we allow for that, but we don't allow, for example, these guys are off. So for example, the permutation table was impossible if we allowed them to have the stock room open still and add things while they were going. So we would put some I would say, natural pedagogical constraints to make it a solvable problem for us. And so one of those constraints would be these aqueous reagents, you know, putting it on the heat here. We don't allow that. These guys are only turned on when you have the subfunnel. But if you want to explore what these guys do under heat and under different conditions, then go to the inorganic lab and go do it there, because we have it all there.
So this applies to the inorganic and the qual stuff, the same type of permutation, things that you guys thought through.
Yes. So in that qual scheme, you notice that I don't think there's anything. The only constraint that we had to add there was once we start adding those reagents, we had to turn off the stockroom and not add a cation, because in our database, that would have been a untenable solution. I mean, we just wouldn't, it would have taken an infinite amount of time to deal with all of those permutations. So we just kind of turned off the cation addition after that. Okay, good. These are great questions. So I'm just kind of telling you what the constraints are that we work under. But in general, it's open-ended. But we do, every lab is different where we have to throw in those kind of constraints. Like I'll show you the quantum lab. There aren't any constraints there. For example, we constrain where the equipment can go. Titrations, you know, sometimes we constrain when you can add things, but mostly it's just for the calculation. All right, let's go do qual. All right, same kind of setup. So here's all of your analytical abilities. And what we have here on the chalkboard are different functional groups, all right, and a general and a known, all right? So you'll see these structures here. What you'll see here is these are what I would call a known, these are knowns. So the student would know what this chemical is. So as they go through and do their wet chemical tests and spectroscopy, they can kind of calibrate themselves and build up some type of trust that their approach is working for determining what is going on, but by knowing these compounds. So if I pick aldehydes, again, I pick the set. So there are these known, so you can see by structure, but the bottle on the right is always an unknown. So you see it's unknown number 210. Same idea, these unknowns are fixed per student. Well, they're randomized to each computer, but they're fixed every time you choose it. So, so what a student would do if they would say, hey, I'm ready to do my unknown, you know, I double clicked, or you can click and drag, and I added this. And so I now drag my round bottom out to my cork ring, and there's my unknown, there's my boiling point and my carbon hydrogen analysis. So now they can just do spectra if they want. If they just want to use spectra and that's how they wanted to determine what's there, they can go do that. There's your splittings. But you also have these wet chemical tests. So we have bromine, permanganate, Jones oxidation, Lucas tests, and so on. We have these different tests. So what you can do is pick an aliquot, put it up here, and see a real picture of what your unknown is. And then I can go grab and do a wet chemical test, and I'll show you either a real picture or a video of that test. So the student has to determine, was it positive or was it negative? And so if time is an important element of interpreting it's positive and gives you useful information about the unknown, then we're going to play different videos. If time isn't important, then we'll just show a picture of the result. So that kind of shows positive Jones oxidation test. Then they can drag this to the disposal bucket, take another aliquot, and, you know, let's go do the permanganate test. So we'll go do that one. And so that's how they can do their qual, and so they can practice. So the question becomes unknowns again. And so in this case, we have, like we said, these numbered unknowns, and And so in these unknowns, they would go through and then they would do the same thing, is they would just report their unknown number and say what compound they have. And then we give you in the instruction manual the table of what the unknowns are. All right. So that's one way. Now, Baylor University has been a big user of these labs for a long time. And they, after 5 years, they ran into an issue where students were, the unknown numbers, the results for the different unknowns were starting to get publicized. And so they, for the inorganic ones, and so they wanted the ability to give unknowns without numbers. And so, so this is the solution that we have for that. Either way is fine. You know, the numbered unknowns are really easy. By the way, we have about 300 unknowns that you can apply. So we have unknowns with these functional groups, and then we have a general unknown, which could be one of any of the 300 unknowns with any functional group or any combination of functional groups. So any of those are possible. So then we have the general unknowns. If I click there, there's that general unknown. The other way is these random unknowns. So I can come over here and say, click on the aldehyde, and then I will give then this unknown so they can say, hey, this is what it is. I can take an aliquot and, you know, I can go do Jones oxidation on this guy and do the result, except notice this one doesn't have a number, all right? Let me show you, like this is a solid, so I can show you melting point. Here's how the melting point works. The melting point comes there, you mouse over it, it's 115. So, so the way you do that is you go back here like we did for the inorganic, you come over here to the lab book, you report, you put in there result, click submit, and it shows them the answer. And then they do the same thing. They're going to come over here, save the file, and then they would upload that, and that would be how they report their unknown. All right, so that's how we do the qualitative analysis. Questions?
Brian, is there a way in the qualitative analysis for students to consider solubility of their unknown compounds? I couldn't find one in the organic chemistry lab bench. I didn't know if there was some way that they could do it in the inorganic chemistry lab bench, or is that just something that was not considered at all?
You mean the solubility of an organic compound in the inorganic lab?
Well,
or the solubility? So obviously in the inorganic lab, it's all about solubility because we have these different anions I can see to see what's soluble and change the pH. But in the organic lab, no, we don't have any, we don't have a set of solvents that they could add to see if it's soluble or not, no.
Okay.
That actually would be an interesting idea, but we have so much on our plate that just makes me feel tired.
Thank you.
Yep.
So Brian, I have a question, please.
Uh-huh.
So now they're going to upload their unknown lab book to Canvas. We use Canvas, and we have to go through Canvas and open up Beyond Labz to actually access those notebooks.
Yeah.
And then we can put a grade.
Yeah, it actually goes really quick. I mean, I'm spoiled because I have TAs and the TAs do it for me, right? But it actually goes really quick. You just, I mean, our LMS, I assume Canvas does the same thing. When we upload the file, it attaches their name to the file name of it. And then you just open up a folder, you download the folder, then what you would do is come in the lab book and come into file and you come into open. And then you'll just see a list of these and you just start double clicking as you go down, open them up, read it. Usually what I do is the lab book has the ability, there's two options. I either tell students to keep 2 copies of lab books, one for their work, if you're interested in what their work was to get to their answer, or just a blank one that just has their answers and makes grading easy. Another option is you can create new pages here. So if this is one page and it can be as long as you want, but you can also create a new page. So you can have page 1 and page 2, and then you can also create a new section. And so here's section 1, here's section 2, and I can come over here and call this section 2, and just have the ability to create sections to help you organize and find where it's at.
Okay. Thank you.
So we have a little bit of time. Let me show you a few things on the general chemistry that I think as you get into fall and next spring, that might be, useful is, so we obviously have a lot of experiments and good simulations of things that you would really do in instructional labs, but we also have some labs that are things that you wouldn't ever have access to. So our quantum lab is one of these. So here's the stock room. So this is my kind of chemistry. I mean, I like all chemistry, but I'm a physical chemist. And so, and here we have sources like lasers and electrons and lights and alpha particles, and we have different kinds of detectors and different types of samples and sample holders and liquids and metals. And then we have these modifiers. And so we have the optics bench, and you can build experiments. So you can take any combination and build this and see what happens. But again, I mean, there's several million of those, but I'm just going to show you some examples. So here's an example of Rutherford. All right. So in Rutherford here, I've got an alpha particle source shooting through gold and being detected here on a phosphor screen. So I can do different kinds of things. I can move my gold away and see my result on my phosphor screen. I could come over here, click on my metals, and pick any one of these 65 metals and show the result. So what happens if I come over here and I do like magnesium, go back here and put it in front? Notice that this changes significantly over gold. So why gold? Why does it do that? I'm just going to come back here to my preset really quick. And then I can start moving my detector screen over here. And so you can see alpha particles. So the idea here is that when we're talking about atomic theory, whether you're an atoms first school or not, when you get to atoms, we almost always take a historical perspective about how we got to where we are in terms of understanding the atom. Our purpose here was to do the experiments that those early scientists had to do, and not just tell them what the result was, but show the student how they came to that conclusion. So just don't have them memorize that Rutherford told us that the atom was mostly empty space, but how he came to that conclusion, and how he also came to the conclusion that the atom was, that the charge of the nucleus was positive, right? And so you can do persist mode and chain, save where these hit. So we have lots of these cool experiments here. Millikan oil drop, okay? I can change my electric field and move my oil drops around. I have, photoelectric effect. I can change the energy of my light coming out of my laser and get electrons to pop out. Or I can use a bolometer to measure their kinetic energy. 2-slit diffraction of photons, change the slit spacing, or change the color and see how that changes things, and change the power that comes out and see how that changes what your pattern does. So lots of cool experiments that are even as sophisticated as Raman scattering experiments that you might use in the PChem course. So I showed you titrations a little bit, calorimetry. What you can do here is, so we have, again, beakers, balances, we have ice, we have an oven. So You have a bomb calorimeter and coffee cup or Dewar calorimeters. We have a drawers full of different metals that you can measure the heat capacity on. Organics, 80 different organics. You can measure the heats of combustion. You got heats of solution, heats of reaction. Again, you got presets here. So, you know, hey, let's talk about heat of solution of ammonium nitrate. So here's my ammonium nitrate. I got my thermometers on. I got a graph showing me temperature versus time. Here's my Dewar. I can go grab my pre-weighed out ammonium nitrate and then see what happens. Hey, it cools. Why does it cool? How can we talk about thermodynamics that way? So you can do Hess's law, talk about entropy measurements, things like that. So lastly, just to wrap this up, we also have gas labs. So we have real gases. So these gases here are based on the most accurate engineering equations of state that we could find for these gases. And then you can pick ideal and real. And then we have these different kinds of chambers. So we have, for example, we have a balloon chamber in here. So here in this balloon chamber, I can go pick, say, carbon dioxide, you know, up my regulator, go add some gas, close it, go in here. Then I can change my units if I want. And I can say, hey, what happens if I just lowered my pressure and blew up the balloon because I went down to a vacuum. So you can have them explore real gases, ideal gases, things like that. So questions, comments?
Yes, Brian, I'm blown away from the amount of work that has gone through making all of these with all the different permutations and everything. Heather gave us a short introductory a couple of days ago, and I asked her about all these simulations that you guys do in the background. And she said that most of it is in that book that I've ordered from Amazon, the one with Beyond, like the one with the says chemistry workbook. But how could you guys fit all these simulations into like such a short book like that? Or I mean, like I imagine there must be tons of simulations that go beyond the, you know, behind the curtain or behind the scene.
Oh, so if I understand your correction, let me see if I can show you. Oops, I don't want to go there. This workbook you're talking about?
Yes.
Okay, so that's a high school workbook that we kind of made for homeschoolers. And so that's kind of geared. So we used to sell a physical workbook when we sold this through Pearson. And actually the first version of the workbook was like 600 pages long because we added so many different kinds of experiments and it was so expensive and daunting that they asked us to reduce it to our favorite 80. So these worksheets right here for higher ed general chemistry that are in these categories, a number about 80 of them, but they're only a small fraction of all the experiments. These lab activities worksheets don't cover even close to everything that it does. These are just basic classic experiments.
So in that, you know, like cation qualitative analysis or the ones that you had on the inorganic side, if you were coming up with all the colors and everything in case we mix different combinations, so can we kind of look them up on your whatever resources that you have, like what reactions or what are those particular compounds that generate those colors, or we don't have access to that?
Let me see. Let me see here. So instructor manuals. Virtual ChemLab. Let's go look at this one. Just easier if I download it really quick. So, if you go all the way to the, so if I sent, this is what I would send. I did include here. So we have another, I mean, now you'd have to remind me, I have to look it up. We have some worksheets that aren't included. There are some paper versions or some PDF versions that aren't branded, that we have some old ones, but we do have some kind of advanced ones, like we have some really cool ones that do de Broglie stuff, and we have reverse photo emission, like shining electrons on the metals to get photons, and so we have all that kind of stuff built into the simulations. But to ask your specific question on the inorganic, for example, so here's for example all of the unknowns, right? The amphoterics number 1, 2, 3, and so on. Here's where you would get the answers. Here's that inorganic advanced. Here's what they are. Here's titration unknowns. But we also have, so we also have these different cation sets. So here is, we have difficulty level 10. So this is the hardest one. This is everything. And this shows an example. There are multiple ways of doing this, but this shows how we could separate the answers to separating and how to identify all of those into different groups. So go see the chlorides, go see, these different groups, and then you go through, and we're going to give you all of these different groups and the key reactions that are needed to do them. So yes, this resource would give you practically all of the different kinds of sets of cations, what the scheme is, and what the reactions are. So we put that together way back. I think we did this back in 2002, I think it was.
Hi. At the start, you mentioned that we could get Word versions of the worksheets. How do we go about doing that if we're interested in that?
Just ask me. I'll send all of that. Just have Nala send me an email, and I'll send it all to her, and then she can distribute to everybody.
Are you that available?
I mean, to us, the worksheets are useless without the software. So we don't care about the worksheets, even though, this has had such a long history. When I first did this, I thought, hey, I'll just make the labs and everybody will write the content. But what we found out is that nobody knew how to write the content. So we had to go write the content. And once we had that, then people kind of figured out how to use the labs and then started developing their own. We have a community site. And if you guys write your own or develop your own stuff, we'd love if you could post that and have other people use it. So, because like you said, this is only a small fraction of what it does.
It's very impressive.
Brian, where do we access the community site?
So that would be community.beyondlabs.com.
Okay.
So, it's not we have these different categories, higher ed, there's places, become members. It's starting to get used a lot, so it's pretty good. All right, anything else?
I have questions, but I want to let others ask questions. I don't want to hog the questionnaire.
Your questions might be questions that we have also.
Okay. Well, this almost looks like a wiki, because I'm going to use this in order to learn things myself, like especially on those reactions and stuff like that. I can teach myself organic chemistry on this.
Yeah, here's the irony of it, right? Is, I'm obviously unbiased, but a lot of people say, well, why teach inorganic qual? Because nobody does it for real. But my argument is that of course no one does it for real anymore, because we have AA emission, or we have all kinds of different spectroscopic techniques. But the issue is it's not about teaching them how to do modern chemistry. It's how to create an interactive environment so that they learn chemistry instead of memorizing chemistry, right? And so by doing the inorganic, by doing all of these permutations, you know, we learned a massive amount of chemistry that I had no idea about. Well, you know, back in 2007-ish, you know, I was doing some research on a DOE grant that we had on aluminas, and you think, aluminas, how boring. I mean, aluminas have been around for, you know, forever, and what new can you learn? Well, it turns out that there's 13 different structures on alumina, and it turns out that a postdoc of mine had developed a solvent deficient route to making nanoparticles of almost any of the transition metal oxides and hydroxides. And in understanding how that worked and the thermodynamics behind it, it all came back to understanding the inorganic chemistry that we figured out just to do the simulation. And so it turns out that for chemical engineers, you know, learning that inorganic chemistry for all your catalytic work is necessary. So I know I'm speaking to the choir, I can tell because of your questions, but it's just really interesting that all of that chemistry there is still relevant. It's just using it in new circumstances where that's where the cutting edge is right now. So I actually got 30 patents just off of that simple knowledge.
Wow. You said something to the effect at the beginning when you started. You said that you are going for like a different platform, different architecture based on your HTML. Is that going to increase the speed? I mean, are we going to, or do you have issues with the speed of the refreshing and so forth, because you access so many databases and stuff?
So these are locally installed. So what you have is a locally installed Mac and Windows version. So speed is not an issue. Okay, we are working toward HTML. This is a prototype of the titration lab. It doesn't do everything that the current lab does. And for example, it doesn't have a balance. You can't do solids. It's all solution based. And we were playing around because before all of this hit, we were exploring India, where there is lots of bandwidth issues. So we needed something lighter that was HTML5 that could work on a phone. So this is a prototype of what we would call a tablet or phone product. But I'll show you kind of how it works. Is still the same engine underneath. Here's a beaker. I can put it where I want. You know, I can grab a pipette, put my pipette here. I could take a chemical, take acetic acid, add it. So maybe you can see how this would be 3 different layers on a phone. This tray comes out on your phone. This is the main thing. You could swipe to get these cards to show more detail. I could then click on my pipette to take it up. I can move this over here. I can now get another beaker, pipette it in. So now that I know it's 25 mils, I can put it over here on my stir plate, turn on stirring, add indicator. So this is an HTML5 version.
I can see HTML work.
So it's working and it's fast. So, you know, we have a pH meter here. We don't have a conductivity meter. You notice we don't have a balance yet. So this is where we're going. It's a bandwidth issue. So unless you think we're getting rich off of anybody, all of this money, where all this revenue gets funneled right back into development for these new things. And but I think what we've decided is that we're going to break this movement into HTML5 into 2 stages. Is we're probably going to convert our current UI UX graphics that you see on the other version, the really highly schemorphic ones, and get that working in HTML5 online first. And then once we get that, we'll move into a lighter version that will work on phones.
Brian, I have a question. The one that you're currently showing, you had mentioned that it might be for tablets and phones. And so it made me wonder, with the current version, is there a limitation for students that would use it on a tablet right now?
You can't, it's a Mac and Windows only version. So you can, so it depends what resources you have at your school and the priority for using those resources. So you can take our Windows version and put it up on a what's called a app server, such as Citrix or Porto or VMware or Apache. There's like 12, 15 of these companies that have the ability to take a Windows app, host it on their server, and then have students access that app on any HTML5 browser, okay? So it would be accessible on a tablet. I think the phone would be too small, but or a Chromebook, it would work on Chromebook. But we don't have the expertise. Other schools have done that, so we know it's possible. We just haven't done it. We just haven't had the bandwidth to learn how to do that, because every school's different. Every school's licensing to different products would be different. And so we just can't afford to be experts in all 15 app server products. But that is a possibility of how to solve the Chromebook issue. We frankly don't see a lot of tablets anymore. We see Chromebooks. So our HTML5 version is getting there so we can solve the Chromebook problem, because it's only going to get bigger, and we're trying to get there.
Yes. When is this going to be available, this system that you have there?
So we are hoping to, we're hoping to get this titration and the inorganic qual ready to be available. So it would be available through it's working. As you can see, we have to hook it into our licensing system and change our content to match it. So you can see here that we have graphs and stuff. So we're hoping in May sometime that we'll have this, and hopefully it will be included as part of the same licensing system. We're not sure about that. We do have an inorganic one. It's all messed up. We're trying to convert the color schemes and stuff. Here's the inorganic one. We're starting to convert colors. So you can see where in purple we've converted to the green, but same thing. Here's my cobalt, here's my chromium, but instead of using real pictures, we're generating an image here. And then I can come over here and add chemicals. So go to sodium hydroxide, come over here to my action, centrifuge it, and then I can decant. And so that's what we're working on. Hopefully May.
So is this, Brian, just being developed so far for your inorganic side? Is there any work on the organic side?
So I can guarantee you that we have products for biology, physics, physical science,
Right.
but 90% of what we're selling right now is general and organic chemistry, and it's 50-50 when it comes to those two. All right. It's fascinating to see on a national level. So again, I guess I'll just be a little arrogant because I'm speaking to the choir. It's amazing to see the personality of the different science disciplines and their acceptance of or willingness to do virtual labs. Chemistry, by far, is much more willing to do a virtual lab, because I think the chemists understand that no one's trying to replace the real labs. We're trying to make real labs better by having virtual labs, whereas physics, by and large, are much more like, oh, it has to be a real lab. It has to be a real lab, and it's slowly changing, but it's just interesting to see the dynamics out on a national level in the science education side of things. So to answer your question about organic, is that 2 years ago, I would have said organic would have been a lower priority, but after this has hit, organic could be the next thing we do, actually. We could stop with titrations in the inorganic and then do the organic and come back and then do calorimetry and then gases and then atomic theory. That's probably the direction we'll go.
I have another question, Brian, and excuse my ignorance. When we were talking about, I heard Amanda, she asked earlier about the version being only for Mac and Windows, and you said, correct, that it is not available for tablets and Chromebooks. Where do iPads fall in that?
iPad's a tablet, so.
Okay, so it's considered a tablet.
Yeah,
Okay.
so you would have
I apologize for that, I wasn't sure.
No, that's fine. You would have to put this onto an app server to get it to work on a tablet.
Okay.
I have done that. It works great. It's just that, you would have to kind of, you either have two choices. You work with your IT people and they do the work and set it up, or you farm it off to another service. Like Porto is an interesting new service where you just say, here's my Windows app, host it for me, and they do all the work, and 2 days later it's available. But it's a per seat license. You're going to have to pay for every student who gets access to it.
So that's different than the licenses that the college has already purchased from you. If we were to put it onto an app server, or would the students still use the current licensing code, just apply it to the app server?
That's a good question, and there's not a simple answer. It depends on how they mirror the app on the server. Some people will say, hey, it's the same app, and so it would take one code to work for X number of students using it. Mm-hmm. And so there's a way of gaming our licensing system that way, if you will, because we couldn't track it. But some services make it look like each student's individual own app, and then they would activate it using our code. So we really, frankly, we just trust everyone that they're going to say, hey, I got 200 students, pay for the 200 students or the 150, and whatever you need to get it into their hands, great. Mm-hmm. All right. And what I would do is I would just encourage to say, hey, you're on a Chromebook, you don't have access to a Windows or a Mac. Okay, here's, I mean, it's really only like less than 5% that we can see right now. Here's your solution for 5%. And if it's a per seat license on these app server companies, then it's really not that expensive.
Okay.
It's a lot cheaper than lab equipment, I'll tell you.
All right.
Going back to your simulations, you demonstrated, like, for example, that titration curve with the pH against volume. And it seemed like it was very correctly following, the weak acid, strong base things. Then that takes me back to the question that I was asking earlier. The Henderson-Hasselbalch equation for that titration curve is very approximate. So are you guys using like other equations to do that in order to be able to, you caught all the rising portion of the curve and everything very nicely? And are those the kind of simulations we can see?
So I mean, you don't see the simulation. It's in our engine that drives our simulation. So for example, if I did a weak acid, strong base one, right? I can titrate or I can mix any acid with any acid or any base with any base. I have triprotic acids and tribasic bases, so I can do any combination of those, all right? And the way we set up the pH calculation is we set up a mass balance, charge balance equation that was a general solution for up to a triprotic acid and a tribasic base, including activity coefficients using the extended Debye-Huckel theory,
Okay.
and adding in partial molar volumes and partial molar volumes, so that the volume mixing is not additive, that we actually take into account the interactions between all of the ions in solution, so that the solution additivity is also correct. So this is about as accurate of a calculation you're going to get.
Absolutely, yeah. But a user like us, we don't have access to those equations to explain some of these to the students. Like say, okay, Henderson-Hasselbalch is too approximate, and these guys have taken it way beyond Henderson-Hasselbalch, and here's the reason why. These are the things. We cannot do that.
Yeah, you can't. Well, it's the same thing. If this was in a real lab, you would do the same thing, right? They would measure it for real, and then you would say, well, this is where Henderson-Hasselbalch fails. This is why it's only good to 3 to 5%, but this one's much more accurate, right? And so I was trying to get to the 10th percent accuracy. The other things that we added in here, for example, is this burette is not a true volume. We have in a random glassware air associated with this burette. So it doesn't produce the exact volume. It has an air built into it. So they can fill it up with water and deliver certain amounts and weigh it using the density, using that it's 25 degrees C. They could then calibrate their pipettes or the burettes. We also include the barometric pressure. So that when you weigh something here, it's the observed mass and not the true mass. Now, the reason we do that is because if you were in a general chemistry non-major class, you know, you wouldn't even tell them about volumetric errors and buoyancy corrections, but their answers would still be wrong. They just would be oblivious, and you account for that in the grading. But if you're teaching a majors class, then you would tell them about it, and the simulation can accommodate for that by doing those corrections. All right, anything else?
Are you guys way ahead of Labster in this?
I was the first virtual lab that ever was made, right? I actually went to Labster in Denmark a couple of years ago because there was a potential investor who was thinking of investing in them, and so they hired me to do evaluation, and you know, I am never going to argue that someone's simulations are not good or anything. I think that there's really 3 of us out there. There's Labster, there's Beyond Labz, and then there's PhET. I think we approach it from 3 different ways, and all 3 ways are valuable. Labster takes the approach of a journey, of a story, and so they try to immerse them in a virtual reality story, but it's a story that's on rails. It has a look of open-endedness, but it's not. You can't go off the rails. You're just allowed to go down this rail in this story. So they provide this, hey, there's been this spill of this rail car. What acid was it or whatever, right? And so it's interesting, but it doesn't allow for all of the permutations, and their engines, I know, aren't as realistic as what we do. Our approach is open-endedness, right? I want to allow for all the different realistic outcomes. I'm focusing on decision makings, and we're going to put the story or the pedagogy outside the lab, outside the software, into these worksheets and lab activities. I'm trying to mimic what we kind of do for real in real labs. And then PhET, PhET is trying to focus on highly focused adjusting one variable at a time, what happens types of things. And so there's nothing wrong with that. It's just a different approach, and you decide what you wanted to do. Labster really is pretty heavily developed on the molecular biotechnology, but they don't have a lot of coverage in chemistry and physics yet. They're also a lot more expensive.
Well, Brian, if nobody has any more questions, I don't want to totally talk over, but I really want to appreciate you in your correspondence and how quickly you've been able to respond to us and help us with our specific needs. I know you have your general webinars and that everybody must be contacting you. Also to work between Nala and myself, and then our district got involved, and then working with SAC directly as well. So we really appreciate all that you've done and feel much more strongly now. I think I speak for my entire department that our students will actually have a sufficient lab experience, even though we've had to jump virtual really quickly. So I really appreciate all of your help.
Thank you. We appreciate it. And, you know, we'll do our best to help you out. Most of it's just fiddling around and figuring it out. And we'll just move forward. I think we've all learned a lot in the last 3 weeks.
Yeah, big time.
You know, for me, you know, because I have my class, you know, I do these webinars and conference calls a lot, but it really, to me, I'm sure you guys are experiencing the same thing. Everything is okay. Everything going online has been okay. The hardest part has been doing a lecture and talking to that vacuum and not being able to see their faces and get a feel for how if they're getting it or not. I just can't solve that problem yet.
Yeah.
Because you can't trust them to say, do you get it? And everyone's silent, right? It's just the hardest thing. I wish we could figure that out. Maybe that's another invention to make some point. All right. Thank you for your time.
Thank you so much. Really appreciate it.
All right. Thank you.
Thank you.
Bye.
Bye.